Hello Kidlets, this is the final part of your notes, so feel free to pause this as you need to. This is also posted on my website, hearthscience.com, and if you look in the left-hand side, you can see where it says subs, click here. That is where your substitute teacher found this video, and you guys are more than welcome to go back and find it and go at your own pace. So last class we had looked at heat in the atmosphere, we've looked at cloud formation, we've looked at surface heating, albedo and absorption and how different materials absorb and reflect light. And we've also we've started to look at sources of pollutants and how we have altered the atmosphere. And this would be another way that you could answer your essential question, because the atmosphere has affected us and we have in turn then affected the atmosphere. But if you're going to answer this way, you would need to cite specific examples, not just say pollution. You have to actually support it. So one of the ways that pollution has altered the atmosphere is through something called temperature inversions. And if you take a look at this image at the bottom right, this is Los Angeles. This is Pasadena. So this is Los Angeles in the late 80s when there was a huge smog problem and a huge pollution issue there. And they've since done a lot of things. There's been a lot of regulations, a lot of laws, a lot of tree planting. They've had a lot of objectives and regulations aimed at making this better. So Los Angeles is not near as polluted actually as it used to be. But what a temperature inversion is when you don't have convection that occurs. And if you remember, convection is that process of heat rising like this, and our cold sinking, and that's a result of density. Remember, like our warm air rises, warm water rises, so that's what convection is. When you have a temperature inversion, this doesn't happen. So instead of having your warm air rising, you have cold air at the bottom. So your warm air is above, like up here, and it's trapping your cold air. So convection doesn't happen. It's inverted, hence temperature inversion. So that cold air is able to hold more levels of pollutants, and it's trapped by the warm air above. And if you look at this picture right here, it actually looks like you see this layer of cloud because it's trapped by that warm air above it that's not allowing that cold to come through and not allowing the smog to move. This can happen for a couple days at a time, and you get this buildup of pollutants. And these are when you get smog alert days. These are really harsh on people's asthma. This can have harsh respiratory effects. When I was growing up, they used to have smog alert days where you weren't supposed to do PE. You were supposed to do PE inside because the air quality was so poor. So this is the temperature profile of what a temperature inversion would actually look like. And we can see that generally what happens is your temperature is going to decrease with altitude in the troposphere. So your temperature profile should look like this. So remember, the higher up you go, the colder it's going to get. Think about what you would wear to the mountains as opposed to what you would wear at the beach. But a temperature inversion, if you see that little stair step right there, naturally you would have this progression where it gets colder. But that little stair step is your inversion, where you don't have a decrease, where you have this stagnation of temperature, where it's staying the same because convection isn't happening. You're not having this natural movement of warm to cold from surface to higher altitude. So here is where you have that. That's what that temperature profile looks like. So looking at some sources of common pollutants, we can see our sources here on the left. So from industry to vehicles, we can see a major recurrent theme here is vehicles and industry. We can see that in almost all of these. Then next to that, we can see some very common health effects. We can see respiratory over and over again here, headaches and fatigues, respiratory, even things like eye and skin irritation that we can see down here. And we can see some environmental effects too. So these can have human effects as well as atmospheric effects. So taking a look at some common pollutants, if we look over here at our bar graph, notice this is an inverted bar graph, and we've talked a bit about being able to read sources of data and interpret that. So this guy is flipped. So some common sources of pollutants, we got carbon monoxide. This is what your smoke detectors are detecting, lead, nitrogen dioxide, and then ozone. Remember that ozone is actually a gas. It is O3. What you breathe is O2. And we want this gas in the stratosphere. We want that higher up because there is where it's blocking UV and it's doing us a service. However, at ground level, ozone is toxic. This can cause, again, a lot of respiratory issues. It's associated with smog. So we do not want ground-based ozone. Ground-based ozone is a source of pollution. Acid rain is another effect of pollution. And if you think of things like graveyards or statues, all of those things are made of a rock that is the same rock that we have in caves, which are highly susceptible to erosion. And if you remember last semester when we did the mineral lab, there was one of those minerals, calcium carbonate, that you dropped water on. It was actually hydrochloric acid, and it fizzled. Well, acid rain is when you have rain that is slightly more acidic than normal rain is, because it is already a little bit higher pH. And acid rain acts to erode those things, and this can have a huge detrimental effect on lakes and streams, all of the organisms within there, because all life has this limited range of pH. And when we have rain that is more acidic from these pollutants in the atmosphere that then combine with the water vapor in clouds, so then you have rain that is containing these toxins where it normally wouldn't have been, then that rains down on all of these organisms. This affects structures as well. This affects forests because it's taking away the nutrients in the soil. So you get this huge feedback loop. And that, again, is our recurrent theme here. So then not only do we get biomass that's dying from the forests being stripped of their nutrients, but that tree death means that we have less CO2 removal. And a carbon dioxide sink is something that takes it in. So trees, forests, and oceans are all huge carbon dioxide sinks. So when we have a large amount of tree death, we have that process that isn't happening. So something that could be taking in carbon dioxide now is not doing that. We can see this in structures like graveyards, marble buildings, even things like the Parthenon in Greece. So here we can see a forest that has been affected by acid rain. We can see that those trees look very dead. Here we can see a large amount of fish that have died. Fish especially are highly susceptible to pH. It changes the pH of the water when you have acidic rain, and it means that they can't breathe. They are more susceptible than most all organisms. Here we can see the statue of George Washington, which has been highly eaten away by acid rain. Here we have the Colosseum in Greece. And here, if we look at this statue from 1908, just looking at the difference in 1969, you can see that you can hardly distinguish any features of that. So ozone depletion. Remember that ozone is not a layer. Ozone is a gas. Again, that is O3, and it's concentrated in the stratosphere. And we have lots of ozone depletion right now, and that is because of a chemical called CFCs, chlorofluorocarbons. And if you take a look at this image, we can see this can. This is an aerosol can. You probably all have these in your house. But up until about 2 decades ago, or 15 years ago, all of those contained these CFCs in them. Those CFCs acted to raise up into the stratosphere, break apart ozone, so you ended up having an O2 and a free oxygen. So suddenly you didn't have O3 anymore. We have O2 and O. So because it split apart the molecule, we now no longer have a lot of the ozone, which was acting to block UV. So if you take a look in your cabinet, maybe you have hairspray that's like this, take a look on the bottle and it will probably say no CFCs. But CFCs specifically are what is breaking apart the gas of ozone. It's not fossil fuels, it's not industry. Ozone is specifically related to this chemical. So there have been solutions that have been proposed. So an alternate would be a PFC that has been proposed to make that O2 and that O reunite back into O3. To my knowledge, I don't think that has happened. But one of the major consequences of this is that we don't have our UV protection. We've seen huge increases in the amount of skin cancer. This harms food. This destroys phytoplankton in the oceans, which is actually the largest carbon dioxide sink. So the ocean and the phytoplankton within it absorb more CO2 than anything else on the planet. So another way that we see this is in the Antarctic, which is significantly colder than the Arctic. Remember, the poles have 6 months of daylight, 6 months of night. So in the spring in the Antarctic, there's been this large accumulation of CFCs over that huge ice-bearing continent. So when sunlight comes in the spring, it activates all of that CFC, the chlorine specifically in the CFCs, and it activates it as the ice crystals in the clouds, and breaks apart ozone. So we have this massive hole in the Antarctic, which is in this image right here. So we can see this is looking at the bottom of the Earth. If you look right here, this is the South Pole. And you can start seeing in the 80s that purple buildup. And what that represents is the depletion of that gas specifically over Antarctica. And this started to be noticed by satellites in the 80s. That was the first time we had polar orbiting satellites at all. So in the lifetime of all of these satellites, we've noticed this continuously depleting Antarctic ozone hole. So that's really where we see that gas being depleted the most. So here we can see an animation of how that happens. So you have factories and homes that are using those products, sunlight that is then activating it, breaking it apart to destroy the gas, and then we can send up weather balloons and things like that to be able to test it. Now, even though the US has banned CFCs, many industrialized nations have not. So this is still something that is being used. So feedback loops is really the culmination of everything we've looked at in the atmosphere, how everything ties together. When we look at things like water, how water can condense in the atmosphere, we can get precipitation, then it can go back into the atmosphere. We get this whole cycle, this entire interaction. And we can see things like this in action when we look at condensing, forming rain, runoff into the oceans, evaporation, collecting in things like rivers to form deposits. So we can see this huge cycle of the water system. We can also see how water can leave oceans in tectonic activity when you have two converging plates and then be released in the atmosphere through volcanoes, and that's how we got our earliest atmosphere, and how we got water in our earliest atmosphere. We can also see this in terms of carbon dioxide. So even though we need carbon dioxide in order to influence our temperature, life has affected the amount of carbon dioxide in the atmosphere as well. So just as we need that oxygen, we then exhale carbon dioxide. And CO2 is crucial to us maintaining a stable temperature. Without any greenhouse gases, the Earth would be freezing. So we want to have some CO2. We need some degree of greenhouse effect. That is actually really important. And then early on, when we started having blooming plants and trees and flowers, we had this accumulation of things that bloomed and died, and we had decomposition, we had more burial, and as things decompose, that's releasing more CO2. So we have this cycling of carbon dioxide as biomass takes it in, as like photosynthesizing organisms take that in, those organisms die, and they re-release that. So we again get this cycling of matter. And through that process is actually how we get fossil fuels, through the process of dead material accumulating, piling up, getting removed from the atmosphere in an oxygenless environment. The level of CO2 dropped, and through heat and pressure, that's how we got fossil fuels. So this is why we can't recreate fossil fuels, because they are created through this long, millions of year process of things being buried, exposed to heat and pressure, and forming those. Another feedback loop would be looking specifically at oceanic carbon. So remember that the oceans take in more carbon dioxide than anything else on the planet, and specifically it's phytoplankton or plankton. And we have so much phytoplankton in the ocean. These are microscopic organisms, and they float at the surface, and they remove more CO2 than all the world's forests put together. We also naturally in the ocean have carbonate rocks. And rocks over millions of years also are able to take in CO2. However, rocks have a very slow rate of sequestering, which means taking in. And it's significantly slower than the carbon dioxide that is produced. So because you end up with an accumulation, we get an increase in salinity. And that increase in salinity, just like an increase in pH or a decrease in pH, can be toxic to organisms within it. So suddenly we have massive amounts of oceanic death, and then we get a decrease in the biosphere, a decrease in the amount of plankton, and then we have less photosynthesizing, CO2 uptaking organisms. So we now have more accumulation of CO2. So more CO2 doesn't just accumulate in our atmosphere, it's removing things that also remove CO2. So we still have, we continue with this cycle of increased CO2. It becomes a vicious cycle. So another thing we get is carbonic acid. So carbon dioxide plus water gives us carbonic acid, and this then can be absorbed by rocks through weathering, and that can contribute to acid rain as well. So our summary of the entire unit, and these would be the things, the major themes that you want to take a look at. So how the formation of the atmosphere happened, looking at those different geologic eras, looking at the formation of life, looking at layers of the atmosphere, the different structures within the layers, how those are differentiated, looking at specific gases in the atmosphere. You had that homework assignment, looking at what the largest concentration of each gas is, looking at phase changes and being able to go each direction and knowing which direction takes in energy, which direction releases, looking at water, the water cycle, water storage, also the carbon cycle, ozone, smog, temperature inversions, and pollutants, looking at the effects of those things in acid rain, black carbon, heat transfer, albedo, absorption, and one thing that is not on here is feedback loops. So that is really putting it all together, some examples of feedback loops. And this all comes back to your essential question of how are we tied to our atmosphere? So these would be some of the many different ways that you could answer that question. And again, what I don't want you to do is say it allows us to breathe. If you put it allows us to breathe, I am going to give you a 0 because a kindergartner could probably say that. This needs to be some new knowledge that you have learned about our atmosphere, maybe about the formation, how we've affected it, how it's changed over time, because we've seen that it drastically changed. We didn't have oxygen for a long time. We had other gases, and then we formed ozone and we formed the greenhouse gases. Thinking about how small changes can have large effects and feedback loops, how internal processes within the Earth, like plate tectonics, like volcanism, affected our atmosphere and life. And then in what ways we are altering our atmosphere as well. And remember, all of these, you would have to give specific examples. So for the essential question, you'll want to choose one specific way to answer. And these are just examples, don't have to use these. And you could all answer many different ways and all be correct. You just have to support it. Pick one way that we're tied and just give some lines of evidence for it. All right, guys, I will see you on Tuesday. Please make sure that you have your packets entirely done. And remember, you can come in for stamps all day Monday, and your study guide needs to be done as well. If you come in and get your study guide stamped on Monday, I will give you some extra credit for it. Have a fantastic weekend. I'll see you soon.